Hello class, today we want to look at intermolecular forces and phase changes. Last class we talked about bonding. Today is intermolecular forces and phase changes. Why are molecules attracted to each other? So in order to look at intermolecular forces of attraction, let's try to find out why, what causes molecules to be attracted to each other. And the answer is intermolecular attractions. These are attractive forces between opposite charges. Remember, it's intermolecular forces, not intra. So we are talking about inter, not intra. Not intramolecule. So class, when we talk about intra, what are we talking about? We are talking about the force that holds the atoms in the molecule. That's not what we are talking about. We are talking about attraction between different molecules. So for intramolecular force of attraction, we have two types, ionic and covalent forces. This is not what we are talking about. We are not talking about these forces of attraction. We are not talking about ionic and covalent bonding. This force holds atoms inside the molecule. We are talking about the force that holds the different molecules. That's what we want to study here. And this intermolecular force of attraction, we have ion attraction, positive ion and negative ion attraction. We have positive end of a polar molecule and the negative end of a polar molecule. Then we even have non-polar molecules with temporal charges. They can cause molecules to be attracted to one another. In intermolecular force of attraction, the charges play a lot. The larger the charges, the stronger the attraction. And the longer the distance between the charges, the weaker the attraction. So these are some of the things that we need to take note as we study intermolecular force of attraction. So let's look at the kind of intermolecular force of attraction we are going to study in this chapter or in this class. We are going to study dispersion forces, dipole-dipole force of attraction, hydrogen bonds, and ion-dipole force of attraction. So these are the four intermolecular forces of attraction that we are going to study. Let's start with dispersion forces. What are dispersion forces? Dispersion forces occur due to fluctuation in electron distribution in atoms and molecules. And this leads to a temporal dipole. That is a region with excess electron density develops a partial negative charge, and a region with depleted electron density develops a partial positive charge. So the attractive forces between this partial negative charge of one molecule and the partial positive charge in another molecule causes this temporal attractive force, which we call dispersion force. Some books call it London forces. And what we have to take note about this force is that since all molecules and atoms have electrons, this force exists in all molecules and atoms. So we can see that, you see this framework, you see the electron, not evenly distributed. Then here it is evenly distributed. But somewhere here, you see, the two electrons have accumulated here, making this side negatively charged, partially negatively charged, and this side partially positively charged. So, because this side is negatively charged and this side is partially positively charged, it affects a nearby molecule. So you see, this positive end attracts electron of this nearby molecule, and you see there is this interaction, this attraction. This is what we call the London dispersion force. And it goes all through the molecules. So it is an instantaneous dipole on one helium atom induce instantaneous dipole on a neighboring atom, which then attracts one another. So this is dispersion force. Because it is temporal, it's weak, but it occurs and it can keep the molecules together. Let's look at the size of a dispersion force. The magnitude of dispersion forces depend on the molar mass. Larger molar masses means more electrons and increased polarizability, leading to stronger attraction. So molar mass, of course, the larger the molar mass, it means more electrons and it means increased polarizability and stronger attraction. The shape of the molecule too has an effect on the strength of dispersion forces. More surface-to-surface contact means larger dispersion force. So you can see here, this is stronger than this. So let's look at this. You see, you can see the effect. You see, this is the molar mass. You see, the molar mass is increasing as you go down the group. And you see its effect on the boiling point. Look at the boiling point. The boiling point is also increasing down the group. And the melting point is also increasing down the group. Even the density is increasing as the molar mass is increasing. So you can see the effect on the physical properties of this molecule. Now we want to look at dipole force of attraction. That's the next intermolecular force of attraction. Polar molecules have a permanent dipole. The permanent dipole adds to the attractive force between the molecules. So on top of the London dispersion force, these molecules have dipole force of attraction, and thus raising the boiling and melting point relative to non-polar molecules of similar sizes. So we see an example. You see this molecule is CH3. CH3. You see, you have a polar. This is partially positive, and this end is partially negative. So you see the attraction. So on top of dispersion force, you have this attraction also. We can see how that affects some molecules. So we have, this is propane. It's non-polar. And look at this molar mass, 44.09. Its boiling point is minus 42 degrees Celsius. And its dipole moment is about 0.08. But we want to look at the next molecule, which is diethyl ether. Its molar mass is almost the same like that of propane. but its boiling point is far larger than that of propane. Why? Because its dipole moment compared to that of propane is higher. So it makes a difference of about 18 degrees Celsius. Then we want to look at ethylene oxide. The same molar mass, almost the same molar mass as propane. But look at its boiling point, because it has a very high dipole moment. Then we look at acetonitrile. Its molar mass is even less than that of propane. But look at its boiling point, 81.6 degrees Celsius. All because of the presence of the dipole moment. Because these molecules are polar, they tend to attract themselves strong. So that is how dipole forces keeps molecules attracted to each other. You can see the reflection in the boiling point. Please, let's just try this. Let me ask you a question. Let's look at this. So choose the substance in each pair with the highest boiling point. We have this class. So we want to look at, so in this question, we are asked to choose the substance in each pair with the highest boiling point. So we have I1 for this and I2. So we want to find out between these two, which one has a higher dipole moment. Please, I want you to look at this carbon. Look at fluorine. This carbon here has the two fluorine atom on the side, and it doesn't have it. And fluorine is the most electronegative element. So this is more polar than this. This one, you see the fluorine, they are oppositely charged. They are opposite, they are staggered. So their polarity cancels. So the dipole for this is 0, but this is polar. So because this is polar, of course, this will have a higher boiling point. I2 will have a higher boiling point. That's why, because it's more polar. Then let's look at this. Please, these two compounds are different. There is no rotation in the double bond, so this compound is different from this compound. And you see here, there's a cancellation. Chlorine has a higher electronegativity, but because it is staggered, it makes this non-polar. But this one, you see the two chlorine on one side, makes this polar. So in this case, this is I1, this is I2. So BI1 will be the most polar, and it's going to have the highest boiling point. So after we have studied dipole force of attraction, please let's look at the next, hydrogen bond. Hydrogen bonding, the bond that occurs in compounds that have the following type of bonds. The compound must have this bond, oxygen-hydrogen bond, or nitrogen-hydrogen bond, or fluorine-hydrogen bond. That is when that compound is capable of having hydrogen bonding. Why is it that the compound must have these three types of bond? The reason is that oxygen, nitrogen, and fluorine are very electronegative atoms. When bonded to hydrogen, they strongly pull electrons towards themselves. They pull the bonded electrons towards themselves. Hydrogen is going there to bond so that it can share electrons and fill its orbital with 2 electrons. But these 3 elements are very electronegative, so they pull the bonded electrons to itself. and makes this hydrogen without electron, without the bonded electron that it has come to share. This results in the formation of a permanent dipole. Hence, hydrogen bonding are a special type of dipole-dipole interaction. It's a special type of dipole-dipole interaction. We are going to see that with water molecule. Let's look at hydrogen bonding in water molecule. So this is a water molecule. Each water molecule has 2 hydrogens, and they have 2 lone pairs. Each water molecule. It has 2 lone pairs. So this hydrogen from this molecule is depleted of electrons because it's bonded to this oxygen. So what happened is that the hydrogen now seeks another molecule with a lone pair and forms an attachment here. So it's this attachment that we call hydrogen bonding. You see, this hydrogen now attaches itself to this electron so that it can have some electron. And so this is what we call hydrogen bonding. So that's how hydrogen bonding occurs. On top of the dispersion force, you have this special type of dipole-dipole force of attraction, which we call hydrogen bonding. Now let's look at some examples. Choose the substance in the pair that is a liquid at room temperature. The others are gases. So for this kind of molecule, so we are going to do the same that we did last time. This is I1, AI1. This is I. So we are searching for oxygen hydrogen bond, fluorine hydrogen bond, or nitrogen hydrogen bond. That's what we are searching for. So if you can see it here, draw its Lewis structure. H, 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 O, H. So you see this molecule has an oxygen hydrogen bond. So it can form hydrogen bonding. Let's check this one. C, H, H, C, H, F, F. This molecule, even though it has hydrogen and fluorine in it, but the hydrogen is not bonded to the fluorine. So this does not have a hydrogen bond, but this hydrogen has a hydrogen bond. So this is going to be the liquid, and this one will be the gas. Let's examine this one also. B1 and B2. We are going to draw the structures, the Lewis structures for this compound. So let's draw the Lewis structure. If you've forgotten Lewis structure, make sure you review that. So that's the Lewis structure. Let's draw the Lewis structure for this also. C, H, H. We are searching for these 3 bonds here. Another C, H, N, H. So each of them should have an octet. So between these 2 molecules, you see that this does not have any of these bonds. It doesn't have any of these bonds, but this has a nitrogen-hydrogen bond. So this is going to be the liquid because it has hydrogen bonding. So to be able to see it, make sure you draw the Lewis structure. So let's continue. So can have hydrogen bonding, and this can have hydrogen bonding. You can see it clearly when you draw the Lewis structure. Now let's look at ion dipole attraction. In a mixture, ions from an ionic compound are attracted to dipole of polar molecules. So you can see this. So this is sodium chloride. You see, it is solvated by water molecule. But look at how the water, it has negative charge. But look at how the water molecules have oriented themselves. They've used their positive end for bonds with the anion in the crystal structure, and they have supplied energy which is enough to break this ion out of its crystal structure. Then when they break it, they solvate it so that it will not be attracted to the cation. So inside this solution, you have charged particles moving in. All that is because of ion dipole attraction. So this is how ionic compounds dissolve in polar solvents. But non-polar solvents cannot dissolve ionic compounds because they cannot form this attractive force. In summary, we have dispersion force. All molecules and atoms have it. It's temporal, so it's the weakest. Then we have dipole force of attraction exists between polar molecules. Then we have hydrogen bonding. The molecules must have oxygen, fluorine bond, nitrogen. The molecules must have the full end bonds. The molecules must have nitrogen-hydrogen bond, oxygen-hydrogen bond, then fluorine-hydrogen bond. They must have these 3 types of bonds for it to be able to have hydrogen bonding. Then we have ionic dipole, exists in mixtures of ionic compound and polar molecules. And the strength increases as you go down the group. So thank you. As we examine the intermolecular forces of attraction, now we want to see how this affects some properties. Thank you so much. So we are going to go into phase changes.